We want to start by reviewing polar coordinates. If I take any point on the xy plane, call it xy, and I said draw a line segment to the origin, we call that distance r. If I set up my little right triangle here, we see there's a Pythagorean relationship, x squared plus y squared equals r squared. And if the angle made with the x-axis we call theta, then we have a simple relationship between x and y and theta as well, and that is that x equals r cos theta, y equals r sine theta. So most of you are familiar when I'm changing something from rectangular coordinates to polar, I make the following substitutions. We are interested in first reviewing area. So let's look at a circle here, and I'm interested in the sector here, a little pie-shaped wedge that comes from the center of the circle. We know there's a very simple ratio here, and that is that theta is to the angle all the way around as area is to the area of the entire circle. So if I solve for a by multiplying both sides by pi r squared, I get area is 1/2 r squared theta, which is a very useful formula and the foundation for finding area under the curve. Now in Calculus 2, we wanted to find the area under the curve, but not in the regular xy system, because our boundaries would be theta 1 and theta 2, and so we converted to polar, and we said we want to find the area of this thing. So rather than vertical or horizontal rectangles, we split this up into sectors. And what we did was we said we had area 1, area 2, area 3, and so on. And so the ith area was 1/2 r of theta I, quantity squared, delta theta I. We added all these up, we took the limit as the norm of the partition approached 0, and we got our area equaled from theta 1 to theta 2, 1/2 r of theta squared d theta. And this was the area we used in Calculus 2 when the region suggested that we should switch to polar, or the integrand suggests that we should switch to polar. Now what we want to do is look at this in 3 dimensions. Now we've got the same region we just did a moment ago, and this is one of our sectors, and let's say this is the ith one and this is the area of this sector. I would like to further subdivide this into other pieces, and let's say that we're looking at the different r's within this one. So I want to find this area here, let's say. So let's call the distance, let's say that's the first r, the second r, the third r, and so on. Let's call this distance right here, from here to here, r sub j, and the distance from here to the first one, r sub j minus 1. Then this would be the jth delta r right here, and I would like to find that little piece. Well, rather than trying to be clever, we can simply take the area of this sector and subtract the area of this sector. So we would get for this little piece right here, which we can now say is the ijth area, would be 1/2 rj squared delta theta I minus 1/2 rj minus 1 squared delta theta sub I. Now it looks kind of complicated, but we can easily factor this. We can factor out the 1/2 and the delta theta, and that would leave us with 1/2 the square of rj minus the square of rj minus 1 delta theta I. And then we notice this is actually a difference of squares, so I can factor this as the product of conjugates. So this would become 1/2 rj plus rj minus 1 times rj minus 1 delta theta. Now, notice this is exactly delta rj. That's exactly what we expected. This, half the sum. That's another way of saying the average. This is simply the average of the r, which we sometimes will just call r bar. So what we've got here now is that the ijth area is 1/2 r delta rj delta theta I. So that means we can write as a double integral our original integral, which was the theta 1 to theta 2, 1/2 r squared d theta we can now do, I'm sorry, there's no 1/2 here, sorry. That's the r bar. We can now do this guy as the double integral from theta 1 to theta 2, 0 to r of theta. And now we're basically going to replace this with r dr d theta. And you notice, after one integration here, we will get 1/2 r squared, which is what we had in Calc 2. So now let's look at the situation where it's actually a three-dimensional problem and we actually have a roof. Now let's suppose I want to evaluate the following double integral, but the region in the xy plane, let's say, is circular. Or this function here involves x squared plus y squared in some capacity, and I realize changing to polar might make my life much, much easier. So we now know we can do the double integral over the same region, and let me loosely call it the r theta, meaning it's the same region, but I'm describing it in terms of r and theta. I simply switch this to f of r and theta, but now the question is, what happens to dA? What happens to my dy dx or dx dy? As we saw in the last example, it's replaced with r dr d theta. So the big difference now, and the most important piece of this puzzle, is when we switch from rectangular to polar, swapping out the variables is easy. Swapping out the instruction is easy. We have developed an extra r term because we saw in the previous step that that shows up in the area. Now, the next video will contain several examples of this.